Imagine a suit of armor that allows a human to fly faster than a fighter jet, survive direct missile strikes, and lift heavy military tanks. It sounds like a fantasy, yet private engineers and military contractors are currently developing the individual components found in these fictional blueprints. To understand how close we are to a real-world Tony Stark, we must strip the armor down to its base systems. We need to analyze the exoskeleton, propulsion, and power sources to find where engineering ends and physics begins. The real challenge lies in the physics of combining these parts. While the individual technologies work, trying to integrate them into a single wearable frame creates an inescapable engineering trap. Modern-powered exoskeletons achieve super strength by using electric motors and force sensors to amplify human movement. Instead of your muscles doing the work, the robotic joints provide the heavy lifting. These systems are already active in the real world, particularly in logistics and medical rehabilitation. They allow workers to move heavy equipment for hours without fatigue and help paralyzed patients walk unassisted. On the digital side, modern AI is beginning to handle some of the specific tasks performed by Jarvis. Modern algorithms can already pilot autonomous drones, recognize faces, and process complex targeting data in real time. If we evaluate these systems individually, we already have the mechanical and digital building blocks required for a functional suit. Human flight has transitioned from fiction to reality through the use of miniature turbine engines. Pilots can now take off vertically and hover by using arm-mounted jets to control their direction. However, these machines face a significant bottleneck: energy consumption. Because jet turbines and heavy exoskeletons require constant power, their operational time is often limited to just a few minutes. This chart highlights the problem of energy density. Liquid jet fuel stores about 50 times more usable energy per kilogram than a standard lithium-ion battery. In the movies, the Arc Reactor solves this by producing massive amounts of power from a device the size of a coffee cup. In the real world, an energy source that small and powerful simply does not exist. Without an arc reactor, any attempt to build a suit requires carrying heavy batteries or large fuel tanks. This added mass leads directly to a fatal engineering flaw. Engineering a single suit requires packing computers, life support, weapons, and fuel into a human-sized footprint. This creates what engineers call a weight spiral. Adding thick armor and electronics makes the suit heavy, which then requires larger jet engines to achieve lift. Larger engines require more fuel to run. As you add more fuel, the weight of the suit increases again, demanding even more thrust to get off the ground. The cycle repeats until the system becomes too heavy to move. The weight of the fuel and engines eventually exceeds the lift it can provide, making the machine mathematically impossible to fly. This integration trap is the fundamental reason Iron Man remains fictional. While the parts work in isolation, they cannot yet coexist in a single wearable package. Based on our current understanding of energy and materials, physics forbids us from building Tony Stark's armor today. Breaking the weight spiral requires a revolution in power generation, such as miniature fusion. Today, fusion research only exists on an industrial scale, requiring massive chambers to function. We'd also need to replace hydraulics with synthetic muscles and use nanotechnology to build armor at the atomic level, stripping away every unnecessary gram. While the complete suit is currently out of reach, the effort to build it drives real innovation. By chasing a superhero blueprint, we develop the very technologies that are already changing lives in the real world.